Good morning or afternoon or evening or whenever you're watching this. I'm going to talk a little bit more about hypothesis tests and what we mean by one-tailed versus two-tailed. We'll see this word or category of words come up here and there. And it's good to know what it means and why we do things a little differently between these two types of tests. So what is a tail? First of all, when we are referring to a tail, one-tailed or two-tailed, we're talking about the graph and which part of the graph is being shaded. So for some tests, we're shading just kind of like the area towards the tail, kind of the end parts of the graph, and we're just doing on that one side, closer to where the z-score ends up being. So this was one that looks like to the left, on the left side, on the lower end of the graph, but sometimes we are doing both tails. So this would be one-tailed, and this would be two-tailed. So the tail is just kind of the ends of the graph where we would be shading typically, and then this one is two-tailed and that one is one-tailed. So then it comes to how do we know how to shade? Which way to shade, when to shade, both tails or one tail or whatever. Well, hopefully we talked about this in class, but the shading has to do with our hypothesis statement. So if our alternate hypothesis is p is less than something, our graph will be shaded to the left of that z-score. If our hypothesis statement is p is greater than something, we're going to shade to the right of our z-score. If our alternate hypothesis is p is not equal to, this is when we shade on the left and right tails. Right? And the reason is if we are testing a not equals to hypothesis, we are interested in, is there evidence of a change in either direction? If we don't think there's a specific direction that our proportion has changed or that we think it's different, we might do a two-tailed hypothesis test, which is basically where we have a not equal to. So it's really just about what our alternate hypothesis is telling us to do. When it's not equal to, we have two-tailed. What this actually means mathematically, though, is that our p-value is going to be double what it would be for a one-tailed test. So let's do an example to see why that happens and how it works out. So in this example, we're talking about proportion of students in high school who have a part-time job. According to the US Census Bureau, it's 0.25. An administrator at a large high school thinks that the proportion is different for the students at her school. She selects a random sample of 200 students, finds that 39 of them have a part-time job. And we want to know, does this provide evidence that the proportion of students with a part-time job is different for students at this school? So different means that I'm testing a not equal to hypothesis. So if P is the proportion of all students who have a part-time job, or all students at this high school, because that's what she's interested in finding out about, we're going to do one proportion z-test. We check our conditions. I'm going to go through this quickly. Given a random sample of students from the school, assume 200 is less than 10% of all students at the school, and 39 of the sample of students has a job, so that would be NP, and then 200 minus 39 would be 161 don't have a job, so that would be NQ. Both of those are bigger than 10, so we can use a normal model. So our hypothesis statements, for some reason I didn't actually put those on the screen, I thought I did, but our null hypothesis, H0, would be that P equals 0.25. So the proportion of students at this high school who have a job is the same as what it is for the whole country. Our alternate hypothesis would be that it's different, that P is not equal to 0.25, because that is what we're trying to test. Not that it's greater, not that it's less, but that it's not equal to. So our alternate would be P is not equal to 0.25. So then when we go to find our z-score, same as always, we do our sample proportion, so 39 out of 200, minus our true proportion, and this comes from the null hypothesis, so 0.25, because we're assuming the null is true for the entirety of this problem, divided by our standard error, right, square root of p1 minus p over n. And in a hypothesis test, as we talked about in class, we do use that true proportion from our null hypothesis as p for our standard error, because we are assuming that to be true. So 0.25 times 1 minus 0.25 divided by n is 200, which gives us a z-score of negative 1.8. So if I were looking at a normal model, right, my mean goes in the middle, which is the true claimed proportion, or what's true for the United States, is 0.25. Our z-score was negative 1.8, which puts us at about here. That's where the 39 out of 200. So our sample proportion was clearly less than the true claimed proportion. So if this were just a one-sided test, if I was just wanting to show that there's evidence that it's less than 0.25, then I would just shade less. But because my hypothesis is not equal to, what I do is I go the same distance on the other side of the mean, and I shade to the right. So the area less than this one over here is 0.0359. I just got that from the z-table. But because I'm doing a not equal to proportion, I'm going to go to the other side, same distance, so positive 1.8 z-score, and shade to the right and add that in as well. Because it's symmetric, that one's area will also be 0.0359, but our p-value ends up being both of those added together, which is 0.0719. So my p-value is double what it would have been if I had just done a one-sided less than hypothesis test instead of a two-sided or two-tailed different than hypothesis test. So our p-values are bigger for a two-tailed, not equal to hypothesis test. One quick side note, when we do this in our calculator actually does that math for us. So there will never be a time if you're using your calculator and going to stat test one prop z test, which is number 5. You are choosing your hypothesis right here. So I'll go ahead and fill this in. P naught was 0.25, meaning that was our kind of claimed value. In our sample, we had 39 out of 200, and we want to show not equal to. So when we go to calculate, your calculator goes ahead and calculates the correct p-value. So you won't ever have to do anything to that. So they got 0.072. Mine's a little off just because of the rounding stuff, but we get the same value. The calculator knows how to do all of that stuff, but it's good to know what's happening in the background and why a two-sided test or two-tailed test, the p-values typically are bigger, and it's harder to reject the null in that situation. I also want to show you, this is a really good visual if it helps you to kind of see what's happening. I always suggest this, use the draw option on your calculator. It kind of shows you those two tails being shaded, so it's a good reminder, and it still gives you the z-score and p-value that we need. So I always advocate for using the draw option. Still gives you everything you need, but we also see visually what's being shaded, which I said right here. Okay, so like always, we would write a conclusion. If we let alpha be 0.05, our p-value is 0.0719 or 0.072, which is greater than 0.05, so we fail to reject. When p is greater than our alpha, we fail to reject the null hypothesis. Never accept the null hypothesis, we fail to reject it. Basically saying we don't have evidence to suggest that our alternate hypothesis is true. So we don't have evidence to suggest that the proportion of students who have a part-time job at this school is different than what it was for the whole United States. We don't have evidence to suggest that it's different from 0.25. Right? So that would be a two-tailed hypothesis test. When we interpret our p-value, right, it's the same idea. We're basically interpreting what's being shaded, right? And finding that area was under the assumption we built a sampling distribution and found a probability based on the null hypothesis being true. So I always start with that, assuming that 25% of the school students have part-time jobs, just like it is for the US. So assuming that the null hypothesis is indeed true, that 25% of the school students have part-time jobs, there's a 0.0719 chance, that's our p-value, that we would get 39 out of 200 students have a part-time job or something more extreme. When we do a two-tailed test, we typically use this wording of more extreme because we're going in both directions. So it's a little harder to say, 39 or more, 39 or less. We're saying 39 out of 200 or more extreme. So more extreme in this sense means as far away from 25% as the sample or even further, because we're shading in both directions. So this would be a great example of how we would interpret the p-value for a two-tailed test. We might use that wording of more extreme as opposed to less or greater. Right? It's kind of a weird thing to conceptualize, but again, for me, the visual helps. So where we're stopping right here is that 39 out of 200. went to the same distance on the other side and were shading out. Right? So something more extreme. So that is just a real quick example of what a two-tailed test is versus a one-tailed test. And yeah, next up in class, we're going to talk about, or I'm sorry, next video we'll be talking about what happens if our hypothesis test is wrong. So look forward to that.